Let's increase the dimensionality of this problem that we just did by 1. So let's go from an area of a circle to a volume of a sphere and show how similar these cases are. So how fast is the volume of a sphere increasing when the radius is, I'll just use the same numbers, 25 centimeters. If the radius is increasing at a rate of 5 centimeters per second. Okay, so extremely similar. Again, the main idea at first is not to suddenly construct the derivatives on the fly. We need first a relationship between the volume and the radius itself. From that, we'll easily follow the relationship between the derivative of the volume and the derivative of the radius. So we need the volume of a sphere, would be the first thing. Okay? So if I remember correctly, the volume of a sphere is 4/3 pi r cubed. Sounds right. All right, what are we trying to find? How fast is the volume changing? They use the word increasing. That's not that important. The point is just that it's changing, not necessarily that it's increasing specifically as opposed to decreasing. How fast is the volume changing? That will be derivative of volume. Again, there's no such thing as fast without time. So dv dt is what we're looking for. So I need to find dv dt, and specifically when the radius is 25. Okay, so that's symbolically what we're going for. And just like before, if I take the derivative d dt now, the derivative with respect to time on both sides, I'll surely end up on the left with what I want here, that particular derivative. And on the right will emerge, because the radius is changing with time, I will get dr dt somewhere over here on the right. And that will be my related rates. Okay, so just related variables, and then take a derivative, and you should get related rates. So these two problems I've shown right here are relatively simple because you're using a formula that you're already aware of, a standard geometric formula for circles and spheres. In other problems, it's not quite as simple because you need to generate the formula sort of on the fly from the way the question is worded and the geometric understanding of the question. So a lot of times pictures help immensely with these types of problems. Not necessary for these two here, but we'll see soon some where the pictures are quite helpful. So dv dt should equal the derivative applied to this side without all of the elaboration that I did for the last example should just be 4/3 pi. The derivative of r cubed will be 3r squared, of course, but to complete the chain rule, I'll have times dr dt. Because remember that r is an inner function inside this composition, right? Cubic on the outside, r on the inside. R is a function of time, because again, the radius is changing with time, particularly at this rate, 5 centimeters per second. So therefore, the chain rule needs to complete this, and we'll get dr dt, in a sense, popping out of the right-hand side. The 3's cancel here, and we end up with 4 pi r squared dr dt. Okay, if we just fill in the pieces now, dv dt, change in the volume, specifically when r is 25, should give us 4 pi 25 squared, I was thinking with the derivative, 25 squared for r squared, and dr dt, again, I use the same numbers, was a fixed 5 value for that derivative. This does not have to be a constant in the problem, it just happens to be in the 2. I've demonstrated here that 5 was the constant value for the derivative of the radius. All right, anyway, to complete the the numbers here. Everybody knows 25 squared is 625. So 625 times 20 should be 12,500, I think. And then you still have the pi there. And now we need the correct units. So again, I could pile all the units in here and make sure it comes out to be the right thing. But I think more easily is to just look at the volume. We were measuring in centimeters. So this should be a centimeters cubed. Right, centimeters cubed, and then the bottom was time. Time, we only saw seconds floating around for time in here, so that should be versus seconds. Okay, so there is the change of the volume of this sphere with respect to time, specifically when the radius reached 25 centimeters. There is a small note here. It's not that important for solving the problem, but it's just something to be aware of for these types of things. Interesting here. You see the area, the change of the area of the circle was related to the change in the radius, of course, which makes perfect sense. So the radius gets larger. The rate at which the radius gets larger has some impact on the rate at which the area increases. That just makes sense. So too down here, the rate at which the radius gets larger implies some sort of change in how the volume is increasing. That just makes perfect sense, right? The volume should get bigger as the radius gets larger. But if you notice the way the expression looks, this 2 pi r is nothing other than the boundary of the circle, right? It's its circumference. Okay, so that even makes some sense, right? That the boundary should control, that this particular proportionality between the change of the area and the change of the radius, that the boundary of the circle should have some sort of role to play in how the area is changing. So too down here, it's not totally obvious, but 4 pi r squared, this is actually the boundary of the sphere, right? Because that is the surface area of the sphere. That's a boundary, the two-dimensional area covering the sphere, right, which holds three-dimensional space inside the sphere, the surface area of the sphere, should have some role in how the volume of the sphere is changing as the radius changes. So just a little geometric note there to be aware of.